Hi everyone, this is Jeff Geisinger and welcome to the next tutorial in the Archsim simulation game tutorial series. In the previous tutorial we went over how to set up some basic geometry in Rhino and input that into the simulation game, apply some envelope and system settings, track area and cost, and then run a simulation using this student simulation game dashboard. And then we saw how that results after running a simulation in some real-time energy or carbon use intensity results, and how those results incrementally build within the Rhino space for each iteration. And in this tutorial, we'll take a closer look at the behind-the-scenes settings that underlie some of these more simplified student games dashboard. So these are going to be the settings that really drive a lot of the inputs and parameters that are set up in the dashboard. And these are settings that are for more detailed control and understanding for the instructor to be aware of. And I'll make this canvas a little bit bigger. You'll see that the instructor settings are divided up into two rows. One of them is the model settings, which I'll go over in this specific tutorial. And in the next tutorial, I'll look at the result settings, which is really going to look at taking the EnergyPlus output results and then converting them into the right units, recording them, and visualizing them. Okay, let's start by looking at the zone settings, which is the first group on the instructor model settings portion of the canvas. You'll see that there's an arrangement of components called Archsim zones, and that's where we'll start. So an Archsim zone is really defined by this one component called a thermal zone, and that's found here in the Archsim tab. Under thermal model, you'll see here there's the thermal zone that creates a thermal zone. It is defined by some settings, which I'll talk about in a second. And a thermal zone is also defined by a BREP, geometry. So we get that geometry actually from Rhino by modeling the geometry in the Rhino space. And then as we saw in the previous tutorial, assigning that geometry to this zone container. So if I turn the preview back on, we've assigned this geometry to this container. I'll turn the preview back off. Now that geometry is input into the BREP end of this thermal zone model. But you'll see that before it goes into that thermal zone model, it passes through this intersector tool. Without going into too much detail about the intersector tool, it's an important component to use in the game because it makes sure that whenever there are faces in the Rhino scene that aren't perfectly aligned, for example, one story of a building overhanging past the other story, it ensures that all of those faces are divided up into individual faces so that EnergyPlus can properly model each surface correctly. So in other words, it'll know when a roof is a roof, it'll know when a shared slab is a shared slab, and when an overhanging floor is an overhanging floor. So this is really important, and I have this set up so that all the BREPs that are selected by the students in the student dashboard pass through this intersection tool, and they will come into the BREP of the thermal zone setting. Now I'll enlarge this canvas again. So the BREPs pass through and enter this thermal zone settings, and you'll see that the next step is then to take it into the zone connectivity network. And so the zone connectivity network would really be used if you had multiple zones in the model. In this case, we only have one zone type, and so it's going into the zone input of the zone connectivity network component. And this is also important for other things such as windows. You'll see here I have my window settings, as well as boundary conditions, which are not coming into play in this game, but this could be like ground conditions or neighboring adjacent buildings that are directly making contact with a wall, for example. Then there's shading, so that would be shading geometry like an overhang over a window or neighboring buildings, and so those go in here. And then we have our optional library settings, which we're using some custom library settings, which I'll talk about in this next group about materials. That all comes into this zone connectivity. So this kind of takes all of the thermal model inputs and brings it together in order to get this output, which is basically your thermal model, and that is what gets set up for running the simulation. Let's take one short step back and look again at the thermal zone component. Now the thermal zone component has settings that we need to give it. And now for the simulation game, the zone settings are located within this clustered component. just to be clear, a clustered component is a simplified group of smaller components that are located within it when you double click on the sender or on the folder icon of that cluster. And you'll see that this contains a series of inputs such as window construction, roof construction, facade construction, and others. And these inputs are, again, if I zoom out, they're tied to these user settings in the student simulation game dashboard, both for the envelope and for systems. So let's take a look at what's inside this clustered zone settings. You'll see that also there's window and zone settings as outputs. So let's take a look and see what is actually making this zone settings cluster. So when you double click on the cluster, you typically get a blue background, and we have a larger number of components. This is made of individual Archsim components. So there are an array of Archsim components here in the Archsim tab. The first one is window settings. You'll see here, actually they're here under settings. If I clicked on window settings, you drop that and you get the same component. I just changed the name window construction here to have the output be legible in the clustered component. So the purpose of this window settings component is really just to take the different types of windows and constructions and be able to get a set of outputs that we can put into the zone settings component. And to keep things simple for the simulation game, all of our window types are external, and so they're set as external here. The other option could be internal, which is an EnergyPlus configuration, but it's not necessary for this game. And the input that we're really in control of right now is the window construction input under window construction. This is actually tied. This becomes an input in the cluster component, and it's tied to the pull-down menu that is in the student game dashboard that we went over in the last tutorial. And so this is really driving the window settings. Those pull-downs, for example, here we have it selected as glazing double argon. That's going to define the type of window that we're going to be using for the simulation, and that is tied to specific material settings and thermal properties that I'll go over later in this tutorial. And that all gets routed through this window construction and is output as window settings. And then you'll see that there's also roof and facade inputs for zone construction. So whatever roof the students choose is going to end up here. Whatever facade they choose is going to end up here. And then we make some assumptions that are always constant throughout the game. These aren't variables that students can choose. So that's for the slab, the partition, and the ground. And so those are three material types that are fixed. They're linked to the library file that you don't really have to worry about. You don't have to change. These inputs make up the zone construction component, which is another input into the zone settings. And then you'll see that there are zone load settings, and these are very important. They define the internal loads for the energy simulation in EnergyPlus. So we have things like, do we have people in the space? What's the density of people within the space in terms of people per meter squared? What's the occupancy? What's the schedule? So what is the occupancy schedule for the zone? Is there equipment, and what kind of equipment density are we seeing? And is there lighting, and what kind of lighting power density are we seeing? As well as dimming controls. And so most of these are actually not controlled by the student. These are constants that we set up for the specific building type. We're assuming that in this round that we're dealing with an office. So an office, we have a set density of people, of occupancy, as well as equipment power density and lighting power density. The only thing that the students can control here is the lighting power density. There's the option to have lower lighting power density, as well as there's the option to have an occupancy sensor, which for the intents and purposes of the simulation game is really just reducing further the lighting power density by 10%. And here you see, if we were to change the lighting power density or the occupancy sensor in the student dashboard, this number would change. It would decrease if we were to turn the occupancy on and the lighting power density lower. And those all get routed here into the lighting power density input. And then dimming controls is another thing that we can control. And that's why I have another what's called a cluster input component. This is making sure that whatever cluster input is hanging out of these individual components, that becomes an input in the component that we see in our larger canvas. And so dimming controls, you'll remember, is another setting that the students have control over, and that they can turn that on or off. and there's a cost associated with that, and that goes in here. And again, lighting schedule is something that is already tied to the occupancy schedule, and it's out of the control of the student. And then the next component within this zone settings cluster is the zone conditioning component. And the zone conditioning settings are located here under the Archsim settings tab. So you'll see that these basically, this toggles that there is heating and cooling. It defines what the heating set point is, and by default we have it set at 20. There's a heating schedule, which is always on. A cooling set point at 24 degrees Celsius, and a cooling schedule, which is also always on. We also have some mechanical ventilation turned on, although that does not necessarily need to be turned on for this model, as well as heat recovery. The heat recovery is actually turned off for this model. You'll see that, so the rest of these, we don't have to really worry about these. These are going to be fixed for the simulation game. So actually everything in this zone conditioning settings component is fixed, and these are inputs that are not controlled by the students. And again, these zone conditioning settings pass into the zone settings component. And then lastly, we'll look at the zone ventilation. Now this zone ventilation component, we're not really controlling ventilation in terms of natural ventilation, but we do need to set infiltration. You'll see that infiltration, which is the second to last input here on the zone ventilation settings component, is set as true. And then our infiltration air changes we have set at 0.3, which is a relatively airtight building. It's representative of new construction, and that is also fixed. That by changing this, we would actually have have significant results in our energy performance. But for the purposes of the simulation game, we have set this as a fixed input for our settings. And then lastly, we have the hot water settings, which needs to be input into the zone settings. The zone settings require an input for the zone domestic hot water, but we're not actually measuring or simulating hot water in our simulation game, so we set that to false, and that's okay. It's input into this zone settings hot water input as false, and it won't come into play in the model, but it does need to be there in order for it to work properly. And so as I mentioned, all of these come into this larger zone settings component, which is located here, zone settings. So you see there's the constructions, there's the loads, the conditioning, the ventilation, and the hot water. And they all come through the zone settings, and they have a zone settings output. So if I zoom out and I go ahead and say discard and close, I don't need to save any changes because I didn't make any changes. But you'll see that this sums up the more detailed internal components within this cluster. We saw all of these different inputs based on those individual components, and then we saw that there are two discrete outputs, window settings and zone settings. And then these settings get sent, the zone settings get sent to the zone, the thermal zone settings input, and then the window settings get sent to the window settings, thermal zone settings component for Archsim. Now we talked about the B-reps that go into the thermal zone. There's also B-reps that go into the window zone, and you'll see that if we trace this input back to the student dashboard, you'll see that the input is set at automated windows. So these are basically automated windows that are generated automatically by Archsim whenever we model geometry. So whenever we actually input geometry into the zone geometry container, windows will automatically pop up, and they'll be, as you remember, their size will be set by the window to wall ratio that we define here in the dashboard. Now, if I go back to the model settings, so those are the B-reps that go into the windows. Later in the tutorial, I'll explain how those parametric windows are actually set up. I'll touch on the generation of those parametric geometries, but for now, we'll just note that that geometry goes into the B-rep for the window settings, and then the window for the thermal zone window component, and then the window settings plug into settings. And now these two come together, as I had mentioned before, in the zone connectivity component. The thermal zone component goes into the zone input in the zone connectivity component, and then the window output goes into the window input for the zone connectivity, the model zone connectivity component. And you'll see that the next input for the zone connectivity is boundary condition, which we're actually not going to be using for the simulation game, but there's a shade input. And so you see the shade is actually linked to another output of the parametric geometry. So there's shading that automatically, as you can see, gets generated whenever we create windows and whenever we have shading actually set. If we have shading set larger than 0 in our student dashboard inputs, then we will get automatic shading generated on windows, and I'll touch on that as we get to that point. But that shading is placed here in the zone connectivity component in order to incorporate it into the overall geometry of the scene. And then lastly, the library is input here through the library editor. And that takes us to the next step of this instructor model settings, which is the library and the materials. So we saw that there are different material settings in the user settings. There are for 3 main materials. There's the roof, the wall, and the glazing. Basically, each material type has a pull down of different options, and each option has an increased performance, like for the example of the roof, higher R value, and then also an increased cost. And just so the instructor knows, you can double click on this pull down menu. It's essentially a value list dialog box. And then the contents of the value list are basically what on the left is what you see in the pull down menu. You see roof underscore R20 and so forth. And on the right is what actually gets input in terms of data downstream. And so here, to keep things simple, I use the same exact naming system, roof underscore R20 underscore R30 and so forth. That naming is actually, it's tied to names of materials that we have in Archsim. And those materials are defined here in the material definitions. And again, as we saw before, these are clustered components. They're clustering a larger array of components that's inside of these clusters that is more detailed than it would clutter up the scene. And so we've simplified them here. And so I can double click on the cluster for the roof, for example, and you'll see that, I'll zoom out a little bit, there are 4 main kind of groups of components, each defining its own roof material type, or roof construction type, and that ranges from roof R20 to R60. And while this looks like highly detailed, really each material is basically made up of, we'll start from the end and move backwards. Each roof is really a construction, and each construction has an output, like we saw in the cluster component. There's an R20 output, an R30 output, and so forth. And that way we can plug all those into the settings, the material settings for our library component. Now, each construction has a name, roof R20, and then you'll remember the right side of our value list, it corresponds to data that is actually the name of the construction that EnergyPlus will use to incorporate it into the thermal model. And so that name is set here, roof R20. It's input into the name of the construction component, and it's referenced in the value list that we were looking at before. You'll see that there's also a layer input, and so that each construction is really just a group of layers, that each layer is a material that's stacked on one on another. The one on the top of the list, you'll see there's a merge component that brings them together. The one on the top is the outside layer, and the one on the bottom is the inside layer, and all the others are in between. And once we stack all these layers together, we get an output that has the U value of the material. This is in standard international units, and we have a cost associated. So how do we actually get these U values, and how do we get the cost? And so we get that as a function of all the layers in the assembly. And so for the roof, we have, from the outside, we have asphalt, and we have some thermal properties associated with that material. All of those properties plug into an Archsim opaque material component, which is located in the Archsim tab. We can plug those in, define them. We can look them up on the internet or on material databases that have density, specific heat capacity, conductivity information about these materials, and we can input them into this opaque material component. And then each material has its own indicators component that allows it to have a cost associated with it, and I'll talk a little bit more about that when we get to some of the materials that have cost. And then each layer is consisting of a material and a thickness. There's a thickness in meters that's associated with each material. So you see for the asphalt roofing, 2 centimeters. For the fiberboard sheeting, there's a specific thickness associated with it, and it also has its thermal properties. And then we get to insulation, which is really the important material in these opaque materials that we're dealing with for the simulation game. You'll see that they have, like the other materials, conductivity, density, specific heat capacity. The conductivity is very important because this is the insulation that is going to be improving the performance of the thermal resistance of this material. And so the lower the conductivity, the higher the thermal resistance. And we're using a conductivity that's a property of XPS insulation. So it's a type of foam insulation. It's 0.034. And we plug that into, again, the indicator component, which allows us to assign a cost to it. I assigned a cost of $0.01 per square meter. This is really just a kind of trial and error cost that I was able to calibrate to provide a kind of a useful or a relationship between material costs that kind of makes sense when we start modeling buildings and running the energy simulation. So this is the cost that kind of pans out for insulation. The bigger our building, or the more surface area of roof we have, the more it will cost. And so this is where that metric actually comes from. And then you see, again, as I described before, there's a thickness for that, and that gets set into this series of layers for the material, and then that eventually gets into the construction. And so below the insulation there's concrete, and below that there's plasterboard finish. And you'll see that for these different materials, I mentioned that there are 4 different roof types. There's R20 through R60. They're all the same except for the insulation changes a little bit. The insulation material itself is the same, but you'll see that the cost and the thickness changes. And the reason why the cost changes in addition to the thickness is because there's additional costs associated with thicker walls like trim and things like that. And that's just to incorporate those bigger differences and to have a little bit more of a comparison for when students start increasing their insulation. They should start noticing an increase of cost. And so I'll just I'll scroll down and zoom into the different types of roofing materials looking at the insulation. So insulation, the R30 XPS has a cost of 0.03 and a thickness of 0.152. And then that increases as we go down. R40, it gets higher, and R60 is the highest. And we see the U value and the cost reflect those changes. So I'll go ahead and close out of this component cluster, and I'll say no. I don't need to save anything because I haven't made any changes. So the walls are essentially the same thing. You'll see that the walls are basically the same arrays of constructions that are consisting of layers, and the only significant layer that is coming into play really for the purposes of the tutorial is the insulation layer. The one difference that we'll see is for windows, and so this is for glazing right here. I'll go ahead and double click on that cluster. And you'll see that there are 4 different glazing constructions. And the baseline is glazing double argon. In a way, these can be thought of similarly to the opaque constructions. They have outputs in order for us to plug them into the library settings component. They have a name, so glazing double argon, which is also referenced in our value list. And they have layers. The only difference is that the layers are glazing layers, which have their own glazing materials that have a few different settings. Like instead of the thermal settings for opaque materials, they're thermal and optical settings for glass. And so that would be like solar transmittance, reflectance, visual reflectance and transmittance, visible light transmittance, as well as infrared emissivity, transmittance and emissivity. And that it becomes very important actually in the definition of a few of our more kind of advanced or more expensive glazing materials. This baseline does not have a low emissivity. 0.84 is a normal kind of high emissivity for a material. So all of the data for our glazing materials comes from the International Glazing Database. You'll see that there are some specific actual manufacturers referenced in the material name, and that's because they're associated with the performance criteria that we're looking for the simulation game for the different tiers of glazing. And so we have basically a sandwich of glazing for these double glazing constructions. We have a sandwich of 2 glass panels, and in the middle we have a gas material, which is located here under materials, gas material. You could right click on gas and set the different type of gas that you want for your assembly. But for all of these we actually have argon. And just like before for the opaque materials, we have to assign a thickness for each of them. And so you'll see that even the gas has a thickness. And those are set in the same way as we did for the opaque materials. And these change as we go along. You'll see that there's a low E coding which has a low emissivity here. The infrared emissivity back is, so it's on the back side. It's on the number 2 surface of the glass, and that's low, a low emissivity coating. I didn't mention for the previous material, but there's also cost that is also calibrated for the order of magnitude of cost of glass when compared to, let's say, the cost of other materials, of opaque materials. And each of these, the different tiers of materials, for example, if I go to the low solar heat gain glass, which is a very high performance glazing that reduces the amount of solar transmission and visible light that comes in, the cost is the highest, but also the visible light transmittance is the lowest. So these are some things that the students will have to evaluate and trade off as they run through their different material testing for their iterations. And so just as before, these material inputs go into the layers and they get merged into the construction component, and then they are output. And so if I close this cluster, you'll see that we have as outputs, again, each material type is an output. Now all of these materials flow into the material editor, into the constructions. I didn't really mention slab and slab on grade because these are basically fixed materials. These are materials that the students aren't really going to have any control over. But just so you know, in order to have a complete model, we need to actually assign material properties, thermal properties and so forth, to the slab on grade and the slab constructions. And so these are basically just concrete slabs. The only difference is that the slab on grade has insulation in it. So I'll close that. All of these materials then go into the library editor, into the constructions input of the library editor. And there are also schedules and materials, but for the simulation game, we're only using the library editor for making custom materials, which go here in the materials input. And then you'll see that there's a library output. And if I trace that back, as I had mentioned before, I go back to my zone settings. My zone connectivity network component actually has a library input, and that's where all that information goes. All the data goes from the library output, which has all of these construction definitions, into this library input. That sets up the thermal model that EnergyPlus will use to run the simulation. So next we'll look at the parametric geometry that I mentioned that actually controls the window and shading geometry that we see in our Rhino model when we select different types of windows or different window to wall ratio and different shading settings. So if I go back to my model again and I go to the user settings, you'll see again if I change the window to wall ratio back to 20, it reduces the size automatically of each face of the windows, of each face of the geometry. And if I change the shading depth, you'll see that the shading automatically updates as well. And so this is defined by basically some Grasshopper settings that are contained within each of these clusters. So let's take a look at the windows first. First, we actually have to create windows, and I'll turn off the shading for now. And so in order to create windows from pure geometry, I'll double click on this cluster. So the first input is actually the zone geometry itself. And so the geometry that we create for our model that we input in the zone geometry container in the student dashboard gets input directly into this container. And then we use a series of operations that take the zone geometry, basically explode it into its individual faces, finds the centroid of those faces, it finds the normal of those faces, and if the normal is pointing horizontally or parallel to the XY plane, it will basically be identified as a wall. If it has a normal that's perpendicular to the XY plane, then this definition will know that it's not a wall, and it will get sent, basically, it won't make it to the next step. Without going into too much detail about each individual component, the data that comes in that tells this component that the surface normals are parallel to the XY plane, and so that they're walls, they actually get output into this A output, which I renamed walls. If the surface normals are perpendicular to the XY plane, like a floor or a ceiling, it gets sent to the B output. And so the A output, or the walls, I then assign to a geometry component, which if I were to preview, you'll see is in Grasshopper, really just the walls. I could turn that preview back off. And now we have to basically we have to create windows from those walls. And so an easy way to create windows is to basically just scale those surfaces. And so we use what's called a uniform scale in all directions. This is a component, a Grasshopper component that our first input, I renamed walls. We just plug the geometry of the walls into that. The next is basically the center of the scaling, and so it's basically the centroid of those walls. And then we need a scale factor. And so that scale factor is going to be defined by the student, by the user. If you'll remember, there are different window to wall ratio options that the students could choose that are right here. And each window to wall ratio is actually, it's not like you're scaling by 20%. There are scale factors that are actually that you apply in order to get a 20% ratio of window area when compared to the wall area. Here are the scale factors. And so those numbers, as you remember, the numbers on the right side are the data that gets input downstream. And to go back to the automated windows chain, you'll see that scale factor is input here, and it is divided by 100, and it's set as a scaling factor. And so here we have the automated windows. I preview that, you'll see that this creates those automated windows, and we have an automated window cluster output. So I'll discard those changes. So those automated windows are output here, and you'll see if I trace that output all the way back, there we go, it connects to this automated windows container. And just as a side note, the students can create their own windows. They could disable this component by clicking this disable key after you middle click on your mouse and you go to the little disable icon. That will turn off those automated windows. And then they could model their own windows and just right click and apply those windows by saying set multiple VREPs. This could be useful if the students want to set, let's say, most of their glazing on the south facade and very little on the north or on the west. So they can model it how they like and then right click here and then say set multiple VREPs. This is already connected to everything, so no new connections need to be made. It's just important to note that if they do want to go back to automated windows, they have to re-enable these automated windows. And it's also very critical to make sure that this is really an either or. You can only have automated windows or custom windows, so be sure to disable the component that you're not using. Okay, so I'll go back to that parametric windows component, and you'll see that there's another small series of components that just basically determine the window to wall ratio. If I double click on that, you'll see that there's just basically the windows come in and we find out what the total window area is. The walls come in here and we find out what the total wall area is, and then we just create a ratio from that. So I will discard that and close. And there's your window to wall ratio. Okay, and then the next parametric geometry is the parametric shading, which is also clustered. And so what that basically does is it takes the window geometry, which is input from the automated windows that we had before, and then the shading depth, which is input here by the depth of shading. So you'll see if I double click on this value list, there's different depth factors, 0 to 1.5. Those are in meters. And if I go back, to this, so based on those two inputs, we basically are able to generate automated shading. And so how is that actually figured out? So I will actually go back and set some shading, let's say 1.5 meters to make it noticeable. And without going into too much detail, you'll see that the windows are set in. We explode the windows and we figure out where the edges of those windows are, and we extrude those windows according to the depth that we have that the students select, and we create a kind of box frame. Let's see if I can preview this. So we create these kind of window boxes, right, that are extruded perpendicular to each window face going outwards and at a depth that the student chooses for their selected shading depth. And so now the next step is really to just get rid of everything except the top surface. And so that's just done in a series of Grasshopper components that basically take that geometry, figure out the normals, and find the normal that's basically pointing up, and culling out everything else. After we do that, we have just the A component. So if I were to bring in the geometry container here, so just the A component of that dispatch gives us the top surface of the window box frame, which is essentially our automated shading. And so I'll discard that and I'll go back to the canvas, and you'll see then that plugs into this automated shading container, which then gets plugged back into the zone connectivity network. So that kind of fills in the zone connectivity network. All right, so next we have to figure out how to actually calculate cost. So cost, you'll remember, it's tied intrinsically to the materials that we use. So you'll see that as I increase the roof R value, the cost goes up. And that's because the Grasshopper file, the simulation game, knows the roof area using an Archsim analysis component. It knows where the roof is, and it knows how much money we're spending. It knows how to apply that roof area, to the cost of each roof component, basically. So the more expensive component, R60, is going to be more expensive because it has a higher cost and it has a higher thickness. You'll see that also the same goes for walls as I increase the walls, and the glazing as well. So if I improve the different types of glazing, you'll see that there's no change between the low E inside and outside. It's really just moving the low E coating on different sides. But you'll see going from the double glazed argon, the baseline, to the high performing low solar heat gain, we have a huge cost uptick. And then lastly, actually, when you change the window to wall ratio, you'll see that also the cost increases. And that's because it's tied to, there's a dollar per square meter factor that is tied to the material itself. And so the more material we have, the more it'll cost. Granted, the less wall we'll have to pay for, but glazing is much more expensive than wall materials, so that's why the cost is, it increases exponentially, or increases more drastically when we increase the window to wall ratio than when we increase the insulation type. But how do we account for costs for the other elements that aren't tied to geometry, like all these system settings? And also, for just this version of the simulation game, the shading depth is actually it's a fixed factor, so it's not really going to increase if you have larger windows, and that's something that might get fixed or changed in the subsequent versions of the game. But so how do we then assign a cost? We know how to assign cost to materials, but how do we assign a cost to these different non-material inputs? And so that is described right here. So we have these two cluster components that take care of that costing. So I'll double click on this one. This cluster component, you'll see, has all these different inputs for occupancy, sensors, lighting, power density, dimming, shading, HVAC. We have inputs and costs, outputs. So I'll double click here. So we basically take the occupancy sensor input from the user setting, and we have that input from, if I go back to the canvas, from these system settings. So the occupancy sensor is on or off. And if I double click here, okay, you'll see that the outputs for occupancy sensor off and on are two numbers. They're either 1 or 0.9. And the reason for that is so that we can have a factor for assigning, for taking into account the effect of the occupancy sensor. So we say the occupancy sensor reduces lighting power density by 10%, if you remember. So with occupancy sensor on, we actually reduce the lighting power density by 0.9. And so we multiply 11 by 0.9 and we get a reduced lighting power density. So if I return to parent and I change the occupancy sensor to on, and I go back to the zone settings, you'll see that my lighting power density is reduced to about 10. So it's about 10%, from 11 to 9.9. Now, how do I get a dollar value out of that? And so this is basically, the name of the game is really just taking those costs or taking those inputs, which are usually like 1s and 0.9s and stuff like that, and running it through some mathematical operation, subtraction, multiplication, in order to get some number that is within the scale of our MIT dollar setup. So roughly we want to have, for these non-material settings, we want to have 0 for a baseline, and then like let's say a 5 or something within that ballpark for turning it on. And so this multiplication and subtraction is really just a way to get from 0.9 to a number like 5. And so you'll see that for the rest of these, it's a similar step of Grasshopper mathematical components in order to get from whatever input number we had from our value list to get an output that is useful or that makes sense for the cost structure of the simulation game. So for lighting power density, it's basically the same thing. We need to get from the two value list inputs for lighting power density, which come in here, which is either 11 or that's the baseline lighting power density, or 9 is low lighting power density. And we just have to establish some kind of mathematical way to get from those two numbers to give us either a 0, or if I go back to lighting power density and switch it to low, how do we get, or in this case, a 3.3. So how do we get from lighting power density inputs, which are either 11 or 9, and get from a 0 or 3.3? Or 3.3. So this is basically also like in the ballpark. We can increase this number in order to make that higher. But we basically, this is just really about getting from some initial values and getting a cost that is within the scale of our simulation game. And the same goes for dimming, as well as parametric shading. And the same goes for the heating and cooling system. So these are really just ways to get some cost values from the kind of inconsistent, slightly unique inputs that we need for the different settings in order for the performance to come in right. But we're able to also utilize those different inputs in order to get some cost values that make sense for our simulation game. And so those different costs get taken to this next cluster, which basically it sums up the costs for if you want to have further analysis of how the model is stacking up in terms of cost. It's not really necessary for the function of the game, but you'll see that there are lists that are associated with the different services in the model and the different costs associated with those services. So you see, for example, there's the one wall service next to one glazing service, and you see that there's a big cost difference between the two. And so this might be useful to identify very expensive parts where you might be spending a lot of money on your model, or finding potential glitches with or sources of high cost. For example, the roof is so highly insulated that we're probably getting not as much of a return on our investment. It's the most expensive component, one of the most expensive components in the project. Although if we were to add up all the glazing, that might be higher. And and then we'll see, you could also see here the cost associated with the envelope only. And so $50 out of 65 is spent on the envelope only. And so that's also useful information, maybe more for the behind the scenes for analyzing the way that you set up the cost for the different materials and settings, but this is useful nonetheless. I will return to the parent. And so the next is really the area analysis, which we use for actually getting the window-to-wall ratio. We use this to find out what the area of, we can find out the areas of the different walls and find out the areas of the windows and get a window-to-wall ratio from that. But it's also useful for getting the area of the model, the actual floor area. So you can see we can add up the external floor, which is the ground floor, with the individual floors in order to get the area of the building. So you'll see that that's actually tied to, this is the area of the building, 3,000, and that's tied to this panel right here. And we know that we know that what we're looking at is correct. We know that what we're looking at is associated with these outputs because we can plug them into a container and test to make sure that our walls are actually showing up the way that we want them to, as well as our ceilings. I'll actually go ahead and, for clarity, I'll turn off the automated windows and the automated shading. So this is very useful to see, to highlight what the walls are to make sure that those are modeled correctly. There are no partitions in the scene, so I don't need to plug that in. Ceilings will basically be the same as floors. And you'll see that there should just be one roof surface. If that intersector wasn't used and we had some overhangs, we would probably have some problems with the roof. Although we have such a simple geometry right now that it's not really coming into play. The external floor should just be that ground floor. And we already looked at floors. And then, yeah, windows we had already looked at. And so this is extremely useful for not only just for the simulation game, but for using Archsim in general. This surface analysis tool is located here in the Archsim bar, located right here in the analysis subtab if you go to surface analysis. And so I'll turn the preview off on that so it's not confused with anything else. And this area analysis then is utilized, as I mentioned, for floor area and for determining some of these other relationships like window to wall ratio. And so in the next tutorial we'll go over these results, so how the results are actually taken into Archsim, into Grasshopper, and how can we start to filter them in order to convert them to the right units for carbon intensity. How can we record our results so that we can record for each iteration the performance and then visualize the performance for each iteration by looking at that bar graph. And we'll look at actually how that visualization component works. And so thanks a lot. Please join me for the next tutorial, and I will see you then.